Hello students, in this video we are going to solve non-homogeneous linear differential equation with constant coefficients. Firstly, let us see how do non-linear differential equations look like. Okay, so see, if I write a differential equation P naught d n time differentiation of y with respect to x plus p1 n minus 1 time differentiation with respect to x p2 n minus 2 y divided by this and so on plus p n minus 1 single differentiation of y with respect to x plus p and y equal to q. This is a non-homogeneous linear differential equation with constant coefficients. Why? Because pi's are constants. Okay, pi's are constants and q is a function of x. Okay, so this equation is non-homogeneous linear differential equation with constant coefficients, right? Now its corresponding homogeneous equation is homogeneous part is p naught dn dxn plus p1 dn minus 1 dx, okay, differentiation of y minus n time plus so on plus p n minus 1 dy single differentiation of y plus p n y. Okay, now we are talking about the homogeneous part. In homogeneous part q x is not present. Okay, instead of it must be 0 here. So this is the corresponding part of given non-homogeneous linear differential equation with constant coefficients, right? So how we are going to solve this? Firstly, I'll tell you one more thing, that we can write this equation into symbolic form also. Okay, symbolic form of given differential equation is, okay, I should tell you directly, okay, it's fine. Now okay, I'm coming to the working method to solve the equation. How to solve these sort of equation I'm going to tell you first. Okay, so how to solve non-homogeneous differential equation. Okay, so see, firstly, first step is you write equation in the symbolic form. Okay, symbolic form. So see, symbolic form means we replace d by dx by capital D. This is known as symbolic form. Clear? So symbolic form is p naught dn, okay, and we write y outside the bracket, okay, plus p1 dn minus 1 plus dn p2 dn minus 2, okay, up to so on, plus p n minus 1 d plus pn. Okay, outside y equal to q, right? Now this thing is also called fdy, okay, fd, okay, not called, because we can write, since this is a polynomial in d, right? So we can write it as a function of d, okay? So we can write it as a fdy is equal to q, because later on we will be coming to the inverse operator. So inverse operator would be, so y could be written equal to 1 upon fd q. This is known as inverse operator of fd, okay? So in this way we would be finding out the solution of this equation, and this solution is known as particular solution or particular integral. Particular integral is 1 over fd into q. And one more thing I would like to tell you here itself. So how we used to solve this sort of equations? We know we also have homogeneous part. Homogeneous part is this, right? We used to solve this part, okay? Homogeneous parts, as we have done in the last video, we can easily solve this part of the equation, and thus we get the solution we get from this equation, from the homogeneous part of this equation, is known as complementary function, right? Complementary function. And also from this non-homogeneous part we find out particular integral, which is equal to 1 upon fd q, okay? And if we add these two solution, we get complete solution. So therefore complete solution of this equation is a solution of the homogeneous part plus particular solution or particular integral, okay? So we write complete solution is equal to cf plus pi, okay? So this is the way how we solve this equation, right? So first method, first step is you write the equation in the symbolic form, okay? Then secondly, do what? Write corresponding homogeneous, okay, corresponding homogeneous linear differential equation, okay, is p naught pn plus p1 dn minus 1 up to so on pn minus 1 d plus pn y is equal to 0. So this is, right, homogeneous part of the linear, this given differential equation. And now you write auxiliary equation. We know we have done this in the last video, right? So now write auxiliary differential equation. So auxiliary differential equation would be p naught dn plus p1 dn minus 1 up to so on pn minus 1 d plus pn is equal to 0. So this is your auxiliary equation, and solve it, find roots, okay? Okay, after finding the roots, from the roots of this auxiliary equation, write down the solution of corresponding homogeneous linear differential equation, which is known as, okay, which is known as complementary function. So from the roots find out the complementary function, okay, or complementary solution, okay? Find out the complementary solution. Okay, so in thus you will be having complementary solution. And then lastly, now do what? Find, okay, you have in third step you are going to find out complementary solution, okay, complementary function. And fourth step you find the particular integral, okay, particular integral. So as I told you, particular integral is equal to inverse operator fd. What is fd here? Fd is this polynomial, right? Fd q, okay. So now, so you have found out complementary function, you have found out particular integral. Now what would be complete solution? Complete solution is equal to complementary function plus particular integral. So this is your solution, okay. So in this way you are going to find out the solution of नॉन होमोजीनियस डिफरेंशियल इक्वेशन. देखो लास्ट में क्या था इन होमोजीनियस पार्ट में क्या था, हम यहीं तक सिर्फ कंप्लीमेंट्री फंक्शन ही फाइंड आउट करते थे बिकॉज क्यू वॉज जीरो देयर. बिकॉज यहाँ पे क्यू अब नॉन जीरो होगा तो देयर फॉर वी नीड टू फाइंड आउट पर्टिकुलर इंटीग्रल फॉर दिस, ओके. तो पर्टिकुलर इंटीग्रल कितना होगा? 1 अपॉन एफ डी इंटू क्यू, राइट. सो बस इतना सा एक्स्ट्रा है, दिस स्टेप इज एक्स्ट्रा इन द नॉन होमोजीनियस पार्ट, राइट. नाउ हमने ये लिखा है 1 अपॉन एफ डी, ये क्या है? वी आर गोइंग टू टॉक अबाउट दिस नाउ. दिस इज नॉन एज, दिस ऑपरेटर इज नॉन एज 1 अपॉन एफ डी, or you can say 1 upon p naught d p1 d minus 1, okay, plus so on plus p n minus 1 d plus pn, okay. इस चीज को हमने क्या बोला है? एफ डी बोला हुआ है, ओके. दिस ऑपरेटर इज नॉन एज इनवर्स ऑपरेटर ऑफ, ओके. This is known as inverse operator of FD, okay, or P naught D1 plus so on Pn तक, okay. This is known as inverse operator of this, right. So some result on these on this inverse operator, okay. Some results on the inverse operator, okay. First result is that prove that 1 by dq is equal to integration q dx. I mean to say, if 1 by d is given, okay, it is nothing but integration, okay. 1 by d ka simple it is, right. If d is the operator, right, okay, d means d by dx, okay. So we know d by d का inverse operator क्या होता है, यानी कि डिफरेंशिएशन का इनवर्स ऑपरेटर क्या होता है? इंटीग्रेशन होता है. सो देयरफॉर बट वी वुड बी प्रूविंग दिस रिजल्ट इन सम अदर वे, राइट. सो प्रूफ सी, लेट डी 1 अपॉन डी इज इक्वल टू टी. ऐसे ले लेते हैं, एज्यूम दैट दिस इज इक्वल टू टी. नाउ ऑपरेटिंग बोथ द साइड विद डी, ओके. 1 अपॉन d q is equal to dt. अब see, 1 by d is the inverse operator of d, therefore they would be getting cancelled and you get q only here. So q is equal to dt. So now q can be written, we know d is equivalent to d is equal to d by dx, right? So t is also here, so dt by dx. Okay, now variable separation, q dx is equal to dt. Now integration, okay, when we integrate, what we get? Dt. Integrating both the side, we get this is equal to t, and we don't know what is q, so it would be remain unchanged. So this implies t is equal to integration q dx. What was t? T was equal to 1 upon dq, right? So therefore 1 by dq is equal to integration q dx, hence the result. Okay, now result 2. Okay, so I hope you get clarity regarding this, that 1 by d is nothing but integration. Okay, so now result 2, 1 upon d minus a q is equal to e raised to power ax integration of e power minus a into q dx. Okay, so see, again we will be proving this in the same way. Okay, proof. See, 1 by dA q is equal to t. Now operating both the side with d minus a, q is equal to d minus a t. Now this would be getting cancelled because they are inverse operator of each other. So q is equal to dt minus at, since dt can be written as dt dx minus at q. So dt dx minus at is equal to q. It is nothing but linear equation. Linear equation किस तरह की linear equation है? dy over dx plus py is equal to, okay. So if we want to solve these sort of equation, how do we solve them? We used to find integrating factor, which is equal to exponential of pdx, okay, and then we multiply this integrating factor y, and this is the solution, right? Okay, integrating factor into q dx. So this is the solution if we want to solve the linear equation, right? So similarly is the case here. So see here, what is p here? P is equal to minus a and q is equal to q. Therefore integrating factor would be exponential of integration minus a dx, which is equal to e minus ax, right? So therefore solution will be integrating factor into t equal to q integrating factor dx, right? So see here, what is integrating factor? Integrating factor is minus ax q minus ax dx, right? Into t भी है. So t can be, if we take this to the other side, we get exponential ax q a minus ax dx, right? So since what is t? T is nothing but this, right? Q. So therefore 1 by d minus a q is equal to eax integration q, this, right? Hence the result. Okay, now one more result. One upon d minus a square, okay, into x, sorry, into exponential of x is equal to exponential ax, okay, is equal to x square by 2 e exponential of x. Okay, it is also very similar to result number 2, right? So therefore I want you to do it by yourself. Okay, I hope you will do this. If you are you won't be able to do this, you just cross check the book and you will come to know, okay, how to solve this, right? So these were the some results on the inverse operator, right? Now we are going to discuss 5 standard cases of particular integral. Okay, 5 standard cases of particular integrals, right? You know, if we want to find out a particular integral, okay, it is not very easy task. Okay, so we will be dealing case by case. In first case, we will be trying to look at the case of when q is equal to exponential. Okay, how to solve the given linear differential equation, non-homogeneous linear differential equation with constant coefficients when q is equal to a exponential of ax. Okay, exponential ax. In second case, or in second rule, we will be discussing that how to solve the differential equation, non-homogeneous linear differential equation with constant coefficients where when q is equal to sin ax. Okay, how we are going to solve in this case, or cos ax. Okay, we will try to look at this in the second case. And in thirdly, we in third case q, we will be saying that how to solve the equation when q is equal to x power something. Okay, and in fourth case, we will see how to solve when q is equal to exponential ax into some other function v, and in last case q would be equal to x v, where v is the function of x. Okay, so turn by turn we will be solving, we will be discussing these cases, right? So firstly we are going to take first case when q is equal to exponential of e raised to power exponential of ax, right? So case 1, okay, or rule 1. Here q would be equal to exponential of ax. Okay, so how to find out the integral, particular integral when q is equal to exponential of ax? So we know particular integral is equal to 1 upon fd q, right? Since q here is equal to exponential of ax, so fd e raised to power ex. Okay, so see, so here let us try to see, okay, how to, what could be this thing. Okay, we know what is fd. Fd is equal to p naught dn plus p1 dn minus 1 up to so on plus p n minus 1 d plus p n, right? This is pn, right? Now what is fd e raised to power x? It is equal to p naught dn ex plus p1 dn minus 1 ex up to so on plus pn minus 1 d exponential ax plus pn exponential ax. Okay, so this is your FD, right? Now you see what could be this term. Okay, what could be this term? So we know dAx means nothing but differentiation of Ex, which is equal to a time exponential Ax. Similarly, d square Eax would be equal to a square Eax. Okay, and so on. Dn minus 1 e raised to power ax would be equal to e raised to power n minus 1 e raised to power ax, and dn e raised to power ax would be equal to an e raised to power x. So we can write it as, so see, fd e raised to power x can be written as p naught. Okay, instead of this we can write a power n e raised to power ax, and instead of this we can write, because this is equal to a raised to power n minus 1 e raised to power ax, plus so on, and this is equal to p n minus 1 a e raised to power ax plus pn e raised to power, there is no differential operator here, so it would be same, right? Now, okay, as you see, nothing has been changed except d has been replaced by a. Okay, rest of the equation is same. So if you write it as, if you take ex exponential ax common, you will be having this plus pn minus 1 a plus pn. Okay, and outside the bracket exponential ax. So if you compare this with fd, which is equal to p naught dn up to so on, so it is pretty similar to fd. Only difference is, instead of a, instead of d, a is here, right? So we can write it as f of a, because it is pretty similar to fd, and instead of d here is a. Okay, so it can be written as f a. So fd exponential ax is equal to fa, and then this exponential ax. So now if we operate both the side by inverse operator, fd eax is equal to 1 upon fd fa ex. What we get? Okay, so this and this gets cancelled, and we are left with ex is equal to 1 upon fd fa eax. Now take it to the, since it is constant, it is some constant because a is constant. Okay, right? So we can take this to the another side, and thus we get f of a ex is equal to 1 upon fd ex. So thus we have solved this integral, particular integral. We can write 1 upon fd e raised to power ax is equal to 1 upon fa eax. So thus if you want to solve particular integral in case of q is equal to ex, what we gonna do? We're gonna replace d by a. Okay, and you will be getting the particular integral by just by replacing d by a, right? And one more thing I would like to tell you here. Okay, uh, if see what is 1 upon fd e raised to power ax is equal to 1 upon a 1 upon fa into exponential ax. If f of a is equal to 0, okay, so this is only true when fa is not equal to 0. But what if fa is equal to 0? So this is undefined in that case, right? So in that case we encountered the failure of the case, right? We will encounter the failure of the case. Okay, and how to solve the non-homogeneous or particular, how to find out particular integral in this case. What we are going to do is 1 upon, if fa is equal to 0, then f, okay, this is also a result. Proof of this result I'm not going to discuss. Okay, this is also a result that if f of a is equal to 0, then 1 upon fd e raised to power ax is equal to x time 1 upon differentiation of this. Okay, differentiation of fd, okay, ex, okay, when f of a is 0. So in that case we will be differentiating this fd with respect to d, capital D. Okay, so what would be, whatever result would be here, like it would be gd. Okay, again we will be putting putting d equal to a. Okay, and we will be finding out the particular integral, right, by putting d is equal to a. So if case fails in the I mean to say, when fa is equal to 0, then we are going to integrate the differentiate the denominator with respect to d. Okay, and again we will be following the same procedure, right? So students, this is it for today. In next video we will be discussing some examples and some problems on this rule first. Okay, on this case. Thank you.